the number that refused to behave. It broke the rules without breaking the math. It followed every law, yet ruined every expectation, and mathematicians couldn't make it disappear. To understand why this number caused so much trouble, we have to return to a moment when mathematics believed it had tamed numbers completely. Whole numbers were orderly. Fractions behaved predictably. Ratios explained the world cleanly. Everything fit. Everything made sense. Then a number appeared that refused to cooperate. It could not be written as a fraction. No matter how carefully it was measured, it never ended, never repeated. Its digits stretched on forever without pattern or mercy. This was not approximation. This was exactness without closure. At first, this felt like a flaw. Surely every meaningful quantity could be expressed as a ratio. Lengths, areas, proportions. Geometry itself relied on that assumption. But this number emerged from simple shapes, from distances that could be drawn, measured, and seen. And yet, it escaped containment. The discovery was unsettling because it was unavoidable. The number did not come from abstract tricks. It came from reality itself, from geometry so basic it predated writing. And once revealed, it shattered the idea that numbers were always neat and obedient. Mathematicians tried to ignore it, to work around it, to hide it behind approximations. But it kept returning more precise each time, demanding acknowledgement. This was the moment math realized something fundamental. Not all numbers wanted to behave, and forcing them to pretend would only create deeper problems. As this unruly number spread through mathematics, it revealed a fracture beneath the surface. If one length could not be expressed as a ratio, how many others existed? The question was disturbing. It suggested that the neat world of fractions was only a small island in a much larger sea. This realization challenged how numbers were understood. Mathematics had long treated ratios as the language of reality. Music, architecture, and astronomy relied on them. Harmony itself was defined by simple fractions. The idea that reality contained quantities that refused ratio felt like betrayal. The resistance was fierce. Some mathematicians denied the number's legitimacy. Others tried to reinterpret it as a limit, a failure of measurement rather than a true value. But every attempt to erase it only strengthened its presence. Proof after proof confirmed the same result. No fraction could capture it. What made this more troubling was how common the number turned out to be. It was not rare or exotic. It appeared everywhere, in circles, in triangles, in growth patterns. Once noticed, it could not be unseen. The conflict deepened as mathematics expanded. These numbers multiplied, forming an entire class that shared the same refusal. They obeyed arithmetic rules perfectly, yet rejected simple expression. The system had not broken. Expectations had. This forced a choice. Either mathematics would restrict itself to what felt comfortable, or would expand to include what felt unsettling. And expansion meant abandoning the belief that understanding required simplicity. The number did not misbehave. It exposed a hidden rule. That reality was richer than the language built to describe it. The conflict reached its peak when mathematicians realized this was not a temporary disturbance. These uncooperative numbers were not exceptions. They were the majority. Most real quantities could not be written as fractions at all. Rational numbers, once thought universal, were suddenly rare. This inverted centuries of intuition. What felt orderly turned out to be fragile. What felt chaotic was normal. Mathematics had been built on a special case and mistook it for the rule. The emotional shock was profound. Proofs had to be re-examined, definitions rewritten. New tools were needed to compare, approximate, and work with values that could never be pinned down exactly. Precision no longer meant closure. It meant control over error. This shift created tension between purity and practicality. Some feared that embracing endless decimals would weaken certainty. Others saw opportunity. New branches emerged, built to handle continuity, limits, and approximation with rigor. Mathematics did not lose precision. It redefined it. The unruly numbers forced math to confront infinity at a granular level. Every calculation became an approach, not an arrival. Exactness existed, but only in principle. In practice, everything was an approximation, bounded by tolerance. This was the heart of the conflict. Mathematics could no longer pretend the world was tidy. It had to learn how to function in a reality that refused to end cleanly. The resolution came when mathematics stopped demanding obedience and started embracing diversity. These numbers were not errors to be corrected. They were signals that reality operated on a broader spectrum than ratios could capture. Once accepted, everything changed. Continuous models became precise. Geometry gained depth. Calculus flourished. The same numbers that once felt like threats became essential tools for describing motion, growth, and change. They allowed mathematics to match the smoothness of the real world, instead of forcing it into rigid boxes. What mattered most was perspective. Precision no longer meant exact representation. It meant reliable approximation. Control over error replaced the illusion of finality. Mathematics became honest about its limits, and stronger because of it. Today, these unruly numbers are everywhere. They shape technology, physics, engineering, and computation. Devices work not because numbers behave nicely, but because mathematics learn how to work with those that don't. The number that refused to behave did not weaken mathematics. It completed it by proving that understanding does not require simplicity, only consistency. So, what do you think? Are we repeating the same mistake again?